Okay, so our last speaker today for a contributed talk is Omar Elashkar. He's the author of the rGenomeTracks package, which was recently released for the Bioconductor 3.14, and he will be telling us about this package today. Go on.
Yeah, thank you, Mahmoud. Hello, everyone. My name is Omar Elashkar. I'm a master's student at Gyeongsang National University School of Medicine at South Korea. And today I'd like to present a small package called rGenomeTracks. But first, I'd like to give you a little bit of motivation about this package. So first, I was trying to visualize the HighC data coming from the topological HighC sequencing. So the biggest project to visualize this kind of data is called Juicebox. So Juicebox main advantage is the real-time zooming. However, though, Juicebox could not be scripted. So maybe Juicebox is quite useful if you're trying to do some kind of exploratory data analysis, but it would be difficult to implement it in some kind of automated workflows. Then I found that there is a package in R called Sushi, and Sushi is very powerful and flexible, and it really supports many different kinds of tracks. However, though, Sushi is built on base R, and also I found that Sushi is slightly difficult. Like maybe that's my subjective opinion, but as Sushi is like quite flexible and has many kind of parameters to tweak, I find it quite difficult to find to easy create a simple figure out of Sushi. However, though, it's worth mentioning that there is that Sushi now has been deprecated in a favor of another package called the Plot Gardener. Plot Gardener, the main advantage of Plot Gardener is using absolute coordinates. And I found it very beautiful package, and I think it shares the same motivation behind rGenomeTracks. Okay, so now on the Python side, we have another package called pyGenomeTracks. pyGenomeTracks is a Python package, a command line tool. This package works by first creating a configuration file with all of the tracks that you want, with all of the parameters and everything. And you just pass this configuration file towards, you pass the configuration file to the pyGenomeTracks software. I found it pretty fast, and it's a pretty interesting project, and it's highly maintainable. However, though, I find the configuration file is slightly difficult to work with because there is no automated way to create this kind of configuration files. And also, I actually don't use Python too much in my workflows, so I prefer something that's written in R. So that's why I really created rGenomeTracks to be an interactive way to implement it within the R workflows. And yeah, I will just like now try to break down the package to see how it is working, and I'd like to receive any of your comments at the end. So this is how, on the left, how rGenomeTracks is exposed to the user, and on the right is how it is working under the hood. So you really, if you want to create any kind of track in rGenomeTracks, you really need only 3 steps. First, you need to create one genome track object of every track you want. So here, these are the 15 tracks supported in rGenomeTracks currently. So for every one of them, you have to create, for every track, you have to create one of these objects. And if you have more than one object, you need to concatenate them together using the plus function. And then you just have to pass the object that you have created to plotGTracks function. And then if you have the plot argument, which is one of the arguments of plotGTracks, if it's set to true, the returned object will be a magic object, and it will be printed to the screen. Otherwise, it will be a passive string. And also, I have to say that plotGTracks calls pyGenomeTracks via reticulate. So it really depends on how do you want to call by genome track environment. So if you're using the, R on a local machine, I'd recommend to use install by GenomeTracks function from the rGenomeTracks package. This function will just install Miniconda if not installed, and then install a custom environment for PyGenomeTracks, or you can even like rename the environment if you want. And then you just have to point the reticulate to this environment before you proceed in your process. But otherwise, if you're using something like Docker, I think it will be easier to just pip install PyGenomeTracks inside of the Docker image. Now, as a breakdown for plotGTracks, it will give you a little bit of better understanding. I'm not showing all of the parameters of plotGTracks. I'm just listing the important ones. Other things you can see in the documentation of the package. So the object parameter is just the genome track object. Then you have to pass the coordinates in chromosome start and end. And the directory parameter is quite important if you don't want to manipulate the image in R further. So if you just want everything to be done by GenomeTracks and export the image at the end, you need to specify their parameter. And there are many kind of files supported like APS, BTF, BNG, and SVG, and etc. And as I said, if plot is set to true, you have to you don't have to specify there. But if plot is false, you have to specify their argument. The other ellipses are all of the ellipses are passed to the. Actually, this is a typo here. All of the ellipses are passed to read image from magic package. So if you want to do some kind of refinements for the magic package for the image that has been imported into R, you can use these parameters from magic package. So here I'm showing a full example for rGenomeTracks in action to show you how it could be powerful. So first here we created a HighC matrix, HighC matrix track. You just pass the file. Depth controls how long the distance between 2 points you want to plot, and minimum value and maximum value represent the minimum value and maximum value on the matrix of the matrix of the HighC, and transform relate to how you want to scale the numbers. And masked bins, this is by default set to false, and this is some point which is technical to the HighC data. So this is just for aesthetic purposes. And the other thing is TADs. So if you are familiar with the HighC analysis, there's a step for TAD for TAD coding. So in this function, you just pass the TAD file, and you can specify the border colors here. And if you want to specify colors like to fill the TADs with specific color, you can do so. And yeah, all of the other parameters you can find on the documentation, but I just want to talk about this interesting parameter here, which is overlay previous. So if you can easily, using this package, overlay different kind of tracks over each other very easily. So this parameter here is share OI. You can just share different, like you can just overlay different tracks on top of each other very easily using this parameter. And then finally, you just have to, I'm here adding the H5 for the HighC and TADs for the TADs or TAD domains. I'm just adding them together to be the object parameter. And then I'm specifying the chromosome, the start and the end. And that's everything to create this kind of figure. So as I have introduced now the rGenomeTracks, I will just give you a little bit of examples for rGenomeTracks in action. However, I have to acknowledge that all of the data and all of the figures here are generated from the pyGenomeTracks project. However, all of these can be easily recreated in the rGenomeTracks. So here are the all tracks supported in the package. So let's start with the first figure here. So the first track here is HighC. This is HighC matrix with the default parameters. And then we have a bit file for the AB compartments. So also it's something related to the HighC analysis. So you don't have to worry if you don't know what does this mean. But I have to say that this bit file has been the parameters of this bit file has been for the display has been set to stack. So you just see all of the annotations of the bed like that stacked in the same line. And also we have the TAD insulation scores. Here the TAD insulation scores are represented as bed graphs. However, there is another method to represent it as a matrix, and I'll show you the example at the end. And also this chromatin states are also bed graphs, and also the display is set to stack. And all of these figures could be actually bigwig or bed graph, but here they are bigwig. And also the DNA methylation here is bed, and all of the annotations here are bed files. And also another thing I want to say about the spacers. So you can, if you see any kind of space between the tracks, you can add whatever space that you want, like a vertical space. And also the axis, you can display the axis either on the top of the plot or below the plot. And also this is another interesting kind of track. This is called the Epilogos. So Epilogos is a way to represent the epigenomic annotation, because mostly the epigenomic annotations, you have some kind of frequencies or some kind of probabilities. So here, this diagram shows one of the epilogos for the chromatin states. So the chromatin states is assigned to bends of the genome, and there is a probability for every bend for a specific annotation or for a specific function on the genome. So here, actually, rGenomeTracks by default only supports the annotation or the annotation names coming from the chromatin states. So if you want to have different kind of annotations, or you want to redefine the color mapping of the annotations, you can use Epilogos JSON function in the rGenomeTracks. And this is a convenience function where you just pass all of the functional annotations that you want, and you map it with the corresponding color maps, and you just pass it to the plotGTracks function. And another interesting thing here is in most of the tracks, you can actually invert it. You can get a mirror image very easily if you want it for some kind of aesthetic purposes or something. You can easily invert it. So we see here the epilogos in specific color map, and also we see the epilogos inverted in a different color map here. Now, this figure is all about the NAGA Peaks. So NAGA Peaks, like peak calling coming from peak calling software like Max. So all of them are actually the same file represented with different parameters. So the first 3 tracks are the traditional peaks or traditional distribution of the peaks. And the other 2 here shows only boxes around the peak itself. And also you can easily specify if you want to see the direction of the peak or the summit of the peak. So here we are showing the summit, and here we are showing the summit of the peak. However, here and here we don't show these summits. And also you can easily remove these kind of annotations if you want the p-values and things like that. Okay, now in this figure we have also HighC matrix and HighC matrix inverted, and now we have also HighC with different color map with the TADs overlaid, and here we have another thing. So here we have the HighC matrix overlaid on it, a bigwig file. And then we have a different kind of track called links. So links is it's like a bit file which just connects 2 points together. So if you want like to connect 2 points together, you can use this kind of track, and you can specify links if you want it to be like this kind of triangle, or it can be some kind of arc, and we see an example like that later. And also here this is just the HighC matrix using the this parameter here. I think this is the show pins. I don't remember what is the name of the parameters, but this is the one, so you can show the pins of the HighC matrix. Okay, now this might seem a little, you might not see this one clearly, but I just will focus on the things that I didn't cover before. So here we have the TADs, but this time the TADs are filled with different colors, and again the TADs inverted. And then we have the bit file, but now this time it's interleaved. So instead of having the chromatin states or the AP compartments on the same line stacked, you can just arrange them on 2 lines like that. And also all of these things we talked about similar ideas before. And here also we have the arcs. So you can see the arcs, and it's in different maps, different color maps. And also we have here the bit files. So actually the bit files, the pyGenomeTracks itself supports different kind of bit files. Either you have the minimal 5 columns or up to 12 columns, the same formula as the bit annotation files. And this is the default value or the default display of the bit files. And also you might notice here, it might not be clear on the slides, but we have here vertical lines. So the vertical lines is not actually a track, but yeah, just for convenience, it's called track v lines. And you just pass a bit file to create these kind of vertical lines. And here, these vertical lines, if you can see, it demarcates the TADs. So it demarcates the area between the compartments. Okay, lastly, this is just the bid graph matrix. So this one is made specifically to show the insulation scores. So I showed earlier the insulation scores as a bid graph, but this bid graph matrix just display the insulation scores as a matrix. Okay, now I show you like a little bit of tricks on how can you implement this kind of use this kind of package in your workflow. So one way to use it is to use reduce. So here I believe this is around 96 files or something like that. So I downloaded 96 bigwig files for the attack-seq data from the TCGA, and I just like created this there's variable to point to list all of the files in the directory that has the pattern of bigwig. And I just applied this list to the track bigwig function. And then I just reduced all of these, like this is a list of genome track objects. So I just reduced all of this list using the plus function to a bid list. And you can just now use this kind of using this argument and pass it to plotGTracks to create this kind of figure. So actually, it didn't take too much time to generate this kind of figure. I think it took like 3 minutes. So this shows how powerful rGenomeTracks could be to create, like to incorporate it in workflows to create big figures like this one. And definitely, you don't have to use only one kind of figure. You can easily like repeat this kind of way to list all of the files using different parameters, like maybe it's bigwig, maybe it's a bit file, bit graph, etc. And you just like easily add them using the reduce function. So I find it to be pretty handy. And this is the last thing. This is actually not a like a native not a native implementation on rGenomeTracks yet. So it's really considered to be a hack. So let's say you don't want to